So moving on. Okay, so this is basically what the X-ray tube looks like. I'll show you a diagram of it as well in a second, but essentially it's a glass envelope which has a vacuum inside it. There's something called the anode and there's something called the cathode, and the anode is attached to a rotor. And we'll go into much, much greater detail about what all these things mean in just a second. So here's a diagrammatic representation of the X-ray tube. So what we're looking at is lead housing. We use lead because the lead absorbs X-rays, and there's permitted levels of dosage for both patients and the personnel who are using the X-ray tube. Within the lead housing, we have the glass envelope, and within the glass envelope is the vacuum. I'll explain the importance of the vacuum in just a second. So within and inside, we have the most important part of the X-ray tube, which is the anode and the cathode. So before I explain the functions of both the anode and the cathode, what they are, etc., I'll just tell you the basic principle which underlies X-ray production. So essentially, it is that when X-rays hit a target material, when electrons hit a target material, uh, X-rays are produced. There's a much more detailed process, and there's a term that you probably heard of, which is Bremsstrahlung radiation, and we will cover this very soon. But today, what we'll be looking at mostly is the construction and working of the X-ray tube, as well as the factors that how do we improve X-ray quality and quantity. And in the next webinar, which is the continuation of this, we'll discuss more about characteristic radiation, types of elements that we use, etc. So to get back to what I was saying, the two electrodes are basically conducting materials. There's a negative one, which is called the cathode. It's made of tungsten, and it's in the shape of a filament, the same filament that you see in your bulbs. And there's also a positive one, which is called the anode, which is also made of tungsten. And the importance of them being positive and negative is that the electrons will travel towards the positive one and away from the negative one. I'm just taking a look to see. Yeah, there's also a semicircle that you'll notice around the filament. This is called the nickel focusing cup. That has, so the function of that is to focus the beam of electrons. A lot of the things which are in the tube are just for getting the best quality X-ray possible. The nickel focusing cup is one of those things. It's made of nickel. You can also see an arrow which says tube current, which we'll get to in just a second and go through in detail. So I think this is what we've just discussed. The only thing that I haven't explained is that as you can see in the diagram, the anode is angled, it's not straight. The usual angle of the anode is between 6 to 30 degrees, 6 to 20 degrees. I'll show you mathematically why this is the angle in just a second. But first we'll look at how the X-ray tube works roughly. So the first step is the heating of the filament. So what happens is that a certain current and voltage is applied to the cathode, which is the tungsten filament. And this produces something called the Joule heating effect, which is where electrical energy is provided to a metal and it gets hot. So the electrical energy is converted to heat energy. Okay, I just see a message in the chat. Okay, that's Asha. Yeah. So, and when the filament gets hot, it starts to vibrate, and these vibrations are so strong that it dislodges electrons from the filament, which then travel outwards. So the temperature at which this happens is usually 2200 degrees Celsius. And this process by which heat causes electrons to leave the tungsten is called thermionic emission. So straight away, we guess one of the reasons for why we use tungsten as the material for the cathode. It's because, first of all, it is able to withstand this huge amount of heat without evaporating, which is one of the most important aspects in the X-ray tube, and something we'll return to again. So what happens once these electrons are released? Before I tell you what happens to the electrons which are released, there's also something I want to mention, which is called the space charge effect. So, as we've discussed in the first webinar, like charges repel and opposite charges attract. So, if a lot of electrons are released by the filament, they can cluster in the space around the filament. And because they're negative, the electrons which leave the filament will not be able to travel through them, and fewer electrons will be produced. This is called the space charge effect. And the main reason why we have the nickel focusing cup is to prevent this from happening. One of the reasons why we use nickel as a material, that semicircle that you see there, is it has a low rate of thermionic emission. So the nickel is not going to be emitting electrons. That's not something we want. All the electrons that we see here are from the tungsten, and the space charge effect prevents electrons from leaving the filament material, but we get around that in various ways. Yeah. So once the electrons have left the tungsten filament, they will be directed into a beam by the nickel focusing cup, and there's a voltage which is applied across the tube. The voltage makes the anode positive and the cathode negative. So the electrons being negatively charged are drawn towards the positive anode. The reason why the glass tube is evacuated, why it has a vacuum inside, is because now the electrons are not running through an obstacle course to reach the anode. The path is completely clear, and they will travel with a very high energy towards the anode. And as I've said here, the focusing cup directs the beam. Now, what happens is that the electrons then collide with the target. So the anode is also called the target material. You'll find those two terms used interchangeably. The electrons collide with the target material at extremely high velocities, which are sometimes half of the speed of light. And due to interactions with the electrons of the target material in the inner shells, X-rays are produced. The X-rays will go through a window in the tube and land on the patient and then form the image. So that's the basic working of the X-ray tube. And now we get into the nitty-gritties of the operation. So the first thing we notice is that there's an electric current being supplied for the tube to work. Now, this electric current will be given by an AC transformer. So AC stands for alternating current. And what this means is that so you might also find that the terms voltage and current are used kind of interchangeably. That's because the voltage creates the current, and the current will also follow the same shape as the voltage. So here in this graph, what we're looking at is actually the voltage which is provided by the AC transformer. Um, so you can see again, it's a sinusoidal wave. So what this means is that the voltage is going to increase, and then you may see it's actually going below the line which says time, which means it's changing in direction. So if you're using an AC transformer, what will happen is first the cathode will be negative and the anode will be positive, as we've seen in this photo, but then it'll go below the line over there and the direction will be opposite. So the electron which was traveling towards the anode will suddenly reverse its direction and follow back to the cathode, which is obviously undesirable. That's not what we want. Which is why the AC current source needs to undergo a process called rectification. Just before I tell you about rectification, just notice there's a note pointing to kVp, which means the peak voltage which is given by the AC transformer. This is an important quantity. We use it to try to figure out how much of voltage is being provided to the X-ray tube. So the process of rectification is where we delete this negative part of the provided waveform. So the AC generator is giving us the voltage in a waveform. It's positive at one point, then it suddenly changes direction. So rectification will remove the negative part of the waveform, but so you'll be left with what looks like a series of hills instead of a series of hills and valleys. Yeah, and the next thing to do is that we want to also eliminate these dips, the hills, the shape. We don't want the shape at all because it's harder to control what's happening in the X-ray tube. So most modern generators, which are called high frequency generators, do a process of rectification by which this waveform, which you see on the left, becomes a straight line waveform. So it's providing a constant voltage in a constant direction, which is exactly what we want in the X-ray tube. And moving on, so how naturally we need to measure this, and the concept that we use to measure is called the ripple. This lets us know how, so if you look at the waveform on the left, it looks like a wave. So the ripple measures how much the waveform is varying, and the formula that we use is V max minus V min by V max into 100 gives us the ripple. And modern generators have a ripple of less than 1%. The smaller the ripple, the better the quality and quantity of the X-ray beam. And all of your X-ray devices in your hospital, the AC generator will be giving you a waveform that looks similar to this. It'll be very nearly a straight line with very little variation, which gives us a high quality X-ray beam, which is what we want. So the next very important term that we have to know is kilovoltage and milliampere. So this is not the, yeah. So the voltage and current, which is used to heat the filament, is of the order of 10 volt and 10 ampere. So volt is the unit which is used to measure voltage. Ampere is the unit which is used to measure current. And kilovolt just means, kilo just means 10 power 3. Again, that's been discussed in the section on units. It's also there in the notes. So the next important thing is the voltage which is applied across the tube itself in order to direct the electrons and give them high velocity so that they will smack against that anode and with as high a velocity as possible. That is of the order of 30 to 150 kilovolts. And also the next important term that we have to know here is the tube current. So the electrons which are released from the filament and which travel towards the anode constitute a current. They're a flow of charges. And it's a very small current. It has a magnitude of 0.5 to 1000 milliamperes. Milli is 10 to the power of minus 3. And these terms will often just be referred to as kilovoltage and milliampere, kV and MA, when you're discussing the X-ray tube. Very, very important terms that we have to know. So the way that X-ray tubes are designed is that the kilovoltage does not affect the milliampere. The X-ray tube is designed so that these two quantities are independent of each other. However, the milliampere, or the number of electrons which are released from the filament, depend on a lot of quantities. They depend on the filament voltage, they depend on the filament current, they depend on the temperature, and so you can see they're all directly proportional. So if the temperature of the filament increases by a little bit, the tube current will increase by a lot. So this is important, the relationship, the quantities on which the tube current depends. So just before we move on to a few more of the details of the construction of the X-ray tube, we'll just briefly touch on why tungsten is chosen as the material for the anode. So tungsten has a very high atomic number of 74, which means more efficient X-ray production by bremsstrahlung radiation. Don't worry about this too much right now. We'll be discussing bremsstrahlung radiation in depth on the next webinar. And very importantly, it has a melting point of 3,370 degrees Celsius, which means that we can give a very high voltage to the X-ray tube without worrying about the tungsten anode evaporating, which would of course destroy the device and stop the X-ray production. So now we're going to look at optimizing the quantity and quality of the X-ray beam which is produced in the tube. So before we do that, let's just look at what it depends on. So X-ray photon quantity means the number of photons of X-rays which are produced in the tube. So this depends on the peak voltage kVp, which we saw from the previous graph on AC generators. It's essentially the voltage waveform which is being provided to the X-ray tube. For modern HF generators, there's no peak voltage. There's just a voltage which is provided. There's no peak because it's a constant waveform. And we see that the beam quantity is approximately proportional to the square of the tube potential. Yeah, so it's proportional to the square. The other factors on which the quantity depends, the voltage waveform, which makes sense. If it has a high ripple, then at one point the electrons will be traveling in one direction and then the other, which will slow down the production of X-rays. This also obviously depends on the generator type that you're using. Depends on the beam filtration. Depends on the distance from the beam. So where you, as we just saw, the intensity is inversely proportional to the square of the distance. So that's why the quantity depends on the distance as well. The exposure time, the amount of time in which you're allowing the X-rays to be exposed, the anode material, and the beam quantity is directly proportional to the current. The Yeah. So just looking at the factors which affect the quality of the X-ray photons. So again, an important factor is the peak voltage. Another thing is the voltage waveform and the filtering or the beam hardening. So there's factors which can decrease the quality of the image which is formed, what we call imaging. So this happens because the X-rays can bounce around in all directions. The X-rays which are produced also don't all have the same energy. So X-rays which don't have enough energy will not contribute to the image, but they will contribute to the page dosage and to the personal dosage. So we do something called beam hardening, which is where we filter out these soft X-rays, which improves the quality of the X-rays. And again, the X-ray photon quality depends on the anode tube. Okay, so now we've looked at the factors which affect the photon quality and the photon quantity. Now what we're going to look at in the last portion of this webinar, the X-ray tubes that we get the highest quantity and also the highest X-ray photon quality. And here, one of the most important aspects is the heating effects on the X-ray tube. So a few important terms is one is the focal track. This is the portion of the anode which is bombarded by electrons. If the anode is a square plate, it'll be a rectangular portion, or I mean, some size. If the anode is a rotating disk, as it usually is, the focal track will be a circular portion. The actual focal spot, which is the physical area of the focal track, which the electrons are hitting on, and the effective focal spot, which is the area of the anode from which the X-ray photons are emitted. So now we come to the line focus principle. So this whole process of constructing the X-ray tube is about minimizing the heat impacts on the different parts while maximizing the X-ray quality. So if the electrons are hitting on a very concentrated portion of the anode, all the energy. Okay, so one important point that you have to remember is that the electrons which are hitting the anode over here are only converting 1% of their energy into X-rays. 99% of the energy of the electrons is being converted to heat, which is given to the anode material. This is a very important point, so I'm going to repeat it again. 99% of the energy of the electrons which are hitting the anode is converted into heat, and it's just expended in heating the anode material. Only 1% of the energy of the electrons is actually used to produce X-rays. So this is why managing the heat from these electrons is really important. So the larger the actual focal spot, the less the heat affects the anode. So if the heat is spread out over a larger area, there's a less of a chance that the anode will be damaged. So that's a good thing. But the problem is that the larger you make the electron beam, the less will be the quality of the image, which is something we understand really naturally because it's kind of like pixel size on a screen. The smaller the pixel, the higher the resolution. So how do we trade off between these two things? We use something called the line focus principle, which essentially what you do is you place the anode at an angle. And what this does is that the anode, the actual focal spot size is large so that the heat is dissipated well, but the effective focal spot size, which produces the X-rays, is and there's a relation to its apparent focal spot size is equal to real or effective focal spot size into the sine of the anode angle. And you can see in the image on the right here. So that image isn't made very well. That C area should be smaller than the A area, basically. But so the anode angle is what we define as the direction between the X-ray beam and the face of the anode. So just repeating that again, the anode angle that we're looking at here is the angle between the direction of the produced X-rays and the face of the anode. So just the points here are just repeating what this is about. Allows for the detail of a small image spot while allowing for heat dissipation. And the angle of the anode normally varies from 6 degrees to 20 degrees Celsius. Not Celsius, just degrees. So let me just show you why that is. So you just need to keep in mind that formula that you that we just looked at. So if we look at sine of 6 degrees, we see that it's 0.2, just ignore the minus sign. And if we look at sine of 20 degrees, we see that it's 0.91. So what happens if we go beyond that is that, just to show you that formula again so that you can relate the two things. So if we go beyond sine 20, the effective focal spot size will become equal to the actual focal spot size, and then it'll actually get larger. So that's why we use these angles, 6 degrees to 20 degrees. It's because we want the effective focal spot size to be smaller than the actual or the apparent focal spot size. So that is the line focus principle, a very important principle in producing X-rays. So another thing that you do to reduce the heat production is use a rotating anode. So you can see here what it looks like. The center, usually you use a molybdenum disc, molybdenum because it has good qualities of heat dissipation, with the edge tungsten, and you direct the electron beams towards the edge. The disc rotates at a speed of around 3,600 RPM. And what you're basically doing is that, so that red line, which is the actual focal spot, the electrons will land on that spot, the X-rays are produced. But if you're doing a long exposure of X-rays, electrons won't keep hitting that spot because the disk is rotating. So the heat will be spread out over the entire disk. So there's more of a chance that the anode will make it. So this is a factor of X-ray tube design. Okay, so when we're talking about when we're talking about how much heat can the anode withstand, or how much heat can the X-ray tube withstand, a really important quantity is the heat unit. So the heat unit is calculated in joules. It's given by this formula: kilovolt effective, kilovolt delivered by the generator multiplied by product of the tube current and exposure time. So I think all of these terms are fairly simple. So if you want to take a screenshot, go ahead. It's an important term. And the reason why the heat unit is very important is because we then use it to understand the tube rating, which is how much of kilovoltage or watts can the tube withstand, and the anode cooling rate as well, which lets us know how much of time to wait between exposures. So you might see a chart like this to understand that. So essentially, if you're looking at this chart, what you'll see on the left-hand side is the stored heat in heat units, which we just looked at. Depends on three factors: the kilovolt, the tube current, and the exposure time. Now, what you'll see here is on top the rated anode capacity. If you go beyond that dotted line, the X-ray tube will not function anymore. We also see a cooling line, which depends. So the relationship is that the rate of cooling is directly proportional to the temperature times 4. All these details will be in the notes. So for now, I'll just explain the concept as well as I can. And we also see, for example, if you want to run it at a load of 200 heat units, 500 heat units, 667 heat units, how long can you run it before the X-ray tube will collapse? As long as you're below that dotted line of rated anode capacity, you'll be fine. But if you're running, for example, if you're running the tube at 667 units for 8 minutes, we see that the line is actually touching the dotted line over there. So that would be a bad idea. Similarly, if you're running the tube if you run the tube for at 500 heat units for 6 minutes, how long do you need to wait for it to cool down? You would look at if you know how much heat units the tube has absorbed, you would look at the cooling curve to know, okay, I've exposed it for 6 minutes. I need to take another image. How long should I wait between the two images to, yeah, so that the X-ray tube doesn't malfunction. So tube rating expresses the load an X-ray tube can withstand. It depends on four things. It depends on the length of the exposure, depends on the size of the focal spot, the actual focal spot, that is, because that's what determines the amount of heat that the anode receives, depends on the anode disk diameter, and the speed of disk rotation. Okay, so moving on to another important effect. This is the anode heel effect. So the anode heel effect acts on the principle of X-ray attenuation, which means that the X-ray is actually not produced on the surface of the anode. They're produced deep within the target material. And as they move their way out of the anode, they get absorbed and attenuated. So essentially what happens is that the angle at which the X-ray leaves the anode determines the intensity. And that's what you'll see on the figure on the left. So the central beam is the beam which leaves the X-ray at 90 degrees. If you go more to the left, which is more towards the anode, you see that the percentage of intensity is decreasing to 80. And as you move more toward the cathode side, the percentage of intensity of the beam is increasing. So this could be applicable in a clinical context if you are imaging two different parts which have different densities. So the higher density part should be placed closer to the cathode because that's where the higher beam intensity is coming from. And the reason for that is that the X-rays are traveling a longer distance through the material towards the anode. So they're getting eaten up by the material. So an important point to notice here is that a smaller anode angle gives us a smaller effective focal spot size, which increases the image quality, but it also gives us a larger anode heel effect. So I'm just going to go very quickly through the last three parts because I think we've gone a little over time. But most modern X-ray tubes are not controlled by switches which turn them on and off because you need to switch between, you might need to take exposures very rapidly. So then you would use a grid controlled X-ray tube, which allows X-rays to be rapidly turned on and off, and a very small voltage to the grid can shut off the tube current. And the construction is as shown in the figure here, which is the glass tube, the anode, the grid, the heated cathode, and the heater. So this is actually considered a 3-electrode setup where the grid acts as the third electrode. The only function of the grid is it's very similar to the nickel focusing cup. It will exert such a strong negative uh, electric force on the electrons that the tube current will be shut off completely. And in this way, by changing the electric forces on the grid, it's an electric switch for the X-ray tube.